Salam. So, this video, we're going to be talking about just pretty much just the idea of what a derivative is conceptually and understanding the limit definition of the derivative. Because I find that, especially with the limit definition of derivative, because where it can be like so tedious to work with, people just kind of memorize the formula, but it doesn't really like sink in as to like what the derivative actually is. And then when you get to problems with like tangent lines or whatnot, then people get confused because they don't have that understanding. And so I think it's really important to just kind of stop and reflect on what are these things that we're calculating? What are these things that we're playing with? And the idea of the derivative is that it's a function. So if you're given some function f of x, then the derivative of that function is is another function which gives you the rate of change at each point of f of x. And so like let's kind of unpack that for a second. So 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 we're given some function f of x. Let me draw this kind of visually. So this is f of x equals x squared. And the rate of change, so like the slope at each point is the values of the derivative. So let me just use like a different color. So like the rate of change here is like the slope um, at that point. The rate of change here is like the slope at that point. And so really what the derivative is it's giving you what the rate of change is at that point in the original function. And and when you have a straight line, you know that the rate of change is the slope. When we have a curve like this, we it's still kind of that idea of slope, but it's not the same because there's not like that same way that you would calculate the slope of a line, like with the y equals mx plus b. Um, it's Instead we calculate it with the derivative because it's changing. The slope of a straight line is the same anywhere you go, and so its derivative would just be a constant, it would be flat. But when we have a function that looks like this, since its rate of change is increasing, then we expect that rate of change to be mapped as a function. And the truth of it is that so for f of x equals x squared, then the derivative of it is is just the straight line. So it would be f prime x equals 2x. And we'll go into that later. But but yeah, so that whole idea is that at each point on this derivative at any x value, it's giving you what that rate of change is, what the slope of this little tangent line is. So the tangent line is the line that touches it at that specific point, and its slope is the rate of change at that point. So if this was like distance over time, then the rate of change would be, speed. If if this was, volume per, I don't know, weight, like the whole idea is that it's just how much f of x is changing given how much x is changing. And that's really what the limit definition is saying. So we know that the average rate of change, um, delta f of x given by delta x, that's how much it will averagely change over some point. So let's say if this is our specific point x and our delta x is like this little interval here, um, then then we can call this one x plus h. So delta x is this distance h here. And so what we're looking at for that rate of change that average rate of change. It's just like that slope of a line. So it's going to be f of x plus h, which is going to be like this point up here. Or sorry, that's not on f. So this point up here, and then like we're making like that average line. So it's f of x plus h minus f of x, which is the difference, like how much f of x is changing in that interval, divided by h, which is how much x is changing in that interval. That's our average rate of change as x goes to x plus h. And so this limit definition of the derivative, all it's saying, so df of x by dx, you know, the derivative, that's what this means, the df by dx, that's the derivative, is equal to the limit of h approaching 0 of this average. So delta f of x plus delta x. So like this big delta, like that's, you know, that's like that average. And then this little d, the derivative, that's it taking the limit. So as this h, you know, slowly goes towards like x and it becomes that tangent line, then that's what our derivative is. And so that's how we get the limit definition of the derivative. So d f of x by dx equals the limit of h approaching 0 of f of x plus h minus f of x divided by h. That's the idea. Like that's where that comes from, and that's how you can understand that limit definition of derivative. So oftentimes, especially in introductory calculus, people really like the Newton notation because, you know, it's just easier to write, which is just the f prime x. And so like this Leibniz notation is the d by dx. And so, but I just find that that's really, that Leibniz notation is really more helpful when you kind of compare it to, you know, that average rate of change, because it's really just showing that it's this rate of change on that infinitesimal unit. It's that limit as the average approaches that one instantaneous spot. And all the derivative is it's giving you the function there. So for example, like let's look at that example that we just had where f of x was x squared. Well then we have that, you know, so I'll write in the Newton notation now. So the f prime of x is it's going to be f of x. It's our limit of h approaching 0, where it's f, the input is x plus h minus f of x divided by h. And so remember what these input things are. So like f of x, that x isn't special, that x is just the input. And so I really tried to emphasize that in like the first video of the series, like the essentials of pre-calculus, because some people, they'll kind of do like f of x plus h, they'll do it as like f of x and then plus f of h, but like that's not the case here. Like this x plus h is just the input. So anywhere in our original function where we would see an x, we're just going to replace that with an x plus h. So since our original function f of x is x squared, then we have x plus h squared. And then we're subtracting off x squared. And the idea whenever you need to calculate something explicitly is you're always going to look for how you can group, how you can factor out the h and then cancel it out with the bottom so that this limit can actually be solved. So so when we expand this guy out, we're gonna get x squared plus 2xh plus h squared minus x squared divided by h. Well, all of a sudden, we'll always see that our original function cancels out, pretty much. Yeah. And then we can always factor out an h now. And factoring out that h is how we can solve this limit. So now this limit, we have that h cancel out with that, and we can just substitute h equals 0, and so this limit equals 2x, and that's the derivative that we calculated up here. And so again, what does that mean? What does the derivative mean? It gives you the rate of change. So if I say, what's the rate of change when x equals 3? Well, it'll be 2 times 3. It'll be 6. 6 of whatever units these functions are. But that's the whole thing, is this, when you're doing this in like physics, you always have units, but right now we're looking at it in its abstract form. So it's just the rate of change. It's how much that our f of x is changing with respect to its input changing. And that is also the slope of the tangent line. So if I say this little tangent line here, at that point, x equals 3, what's its slope? Well, its slope is 2 times 3, it's 6, because it's given from that derivative. And yeah, and that's the last thing I want to mention for this video is the tangent lines. Because in order to solve for the equation of a line, you only need like 2 pieces of information, either like 2 points or a point and a slope, or the slope and the y-intercept. So we know the equation of a line is y equals mx plus b. This m is always going to be given by the derivative at that point. So if we say, what's the tangent line? What's the tangent line at x equals 3? Well, this m is always just going to be f prime at that point. So f prime at 3. And then this b, we're just going to solve it by subbing in the other piece of information we know, which is we'll always know the point. So since a tangent line touches the function at that point, it will always go through the point of, so let's say we're looking for the tangent line A, or here we're keeping the example as 3, then it will always have that point 3 f of 3 that's going through it. And so in general, to solve for this form for the equation of a tangent line, you'll always have, so let's say tangent at x equals a, then we'll have y equals f prime a times x plus b, and then we solve for b by subbing in the point that we know it touches. So we know that this will go through f of a when x equals a. And so that means that b equals f of a minus a times f prime a. And so the equation of the tangent line is always just going to look like y equals f prime a times x plus this y-intercept, which is f of a minus a f prime a. And yeah, and just the point to emphasize here, because I find some students will get a confusion about solving for tangent lines, is again, what is that derivative? That derivative is that rate of change. It's that slope of the tangent line. And it'll pass through at that same point. So given two pieces of information, you can always solve for a line that way. Um, but yeah, this is really what I wanted to emphasize for understanding the definition of the derivative. And also, yeah, this last step here, like when you're substituting in that x plus h, just make sure that in your original function, if it was given as f of x, that x is the input. So anywhere where you see that, you're just going to replace that with x plus h, because that's something that people will make mistakes on. So yeah, this is it. I hope this was helpful. If anyone is having, a difficult time with understanding the definition of the derivative, I really hope that this brings like some clarity to it. Uh, in first year calculus, there's always going to be like at least one, maybe like two, like there's always going to be a couple questions on your exam that's just use the definition of the derivative to solve this. And so it's just important to have that foundational understanding of what actually is the derivative, and then the definition of it, it just seems to make more sense. So I hope that helped with this. There's Yeah, if there's any questions, anything I didn't say that clearly, hopefully you can just leave a comment and I'll try to respond to it to the best of my ability. But you